Hello students, in this video we'll prove Wirtinger's inequality. Wirtinger's inequality is an integral inequality. We can also call this the Poincare inequality if we wish. One of Poincare's many inequalities. And what it says that if f maps 0 to pi, it doesn't have to be 0 to pi, it can be any interval, is smooth, and vanishing on the boundary, that of course just means that f of 0 is equal to f of pi is equal to 0, okay? Then we have the following integral inequality. Then we have that the integral from 0 to pi of f of x squared is less than or equal to the integral from 0 to pi of f prime of x squared dx. So what this says, if we put this in the parlance of LP space theory, this says that the L2 norm of the derivative exceeds the L2 norm of the original function as long as the function is smooth and vanishes on the boundary of the region, right? And if it's a compact region and the function is smooth enough, this inequality should persist in higher dimensions too, maybe with different constants here based on the diameter of the region. Okay, so that's the inequality. It's either due to Wirtinger or Poincare, whoever you wish. Okay, and so here's the idea to prove it. We're going to construct an auxiliary function, so what we're going to do is we're going to build, so set g of x to be f of x over sine of x, okay? Now since f is smooth and vanishes at the origin, I know it vanishes at least to order 1, so this function g is defined at 0 and it's defined at pi because f has the right sort of order of magnitude smooth. So I can Taylor expand to pi. I know that sine vanishes to order 1 at 0 and sine vanishes to order 1 at pi. So this function g is well defined on 0 to pi. Well defined. Okay, great. And so now, let's look at the integral from 0 to pi of f prime of x quantity squared dx. Well, it's going to be the integral from 0 to pi. And then I'm going to do what is f? It's going to be g prime of x sine of x plus g of x cosine of x quantity squared dx. Okay, just by foiling it out. And so now I'm going to have three sorts of terms over here. So the first term we're going to see is this is equal to the integral from 0 to pi of g prime squared sine squared, g prime of x squared sine squared of x dx. Plus I'm going to have two copies of this, to the integral from 0 to pi of g of x, g prime of x, and then sine x cosine x. And then dx, of course. And then the last terms over here are just going to be plus the integral from 0 to pi of g of x quantity squared cosine of x squared dx. Okay? And so now here's the kicker. I'm going to integrate this by parts over here, this middle integral. So over here, when we integrate by parts, this over here, so I have a 2 times this thing over here, that's going to be my dv, and that's going to be my u over there when I integrate by parts. So let's do this. It's going to be the integral from, this is equal to the integral from 0 to pi, g prime of x quantity squared sine squared of x dx, okay? Then plus what? Then plus the boundary terms. So the antiderivative of v is just going to be g squared. So it's going to be g of x squared sine x cosine x from 0 to pi. Those terms are going to vanish, obviously. And then minus the integral from 0 to pi of v, which is g of x squared, and then du. So the derivative of u is just going to be, well, this of course is, u is really just 1/2 sine of 2u. So the derivative of this is just going to be cosine of 2u, and cosine of 2u is cosine squared of x, or cosine of 2x, of course, right? Cosine squared of x minus sine squared of x. That's a double angle formula for cosine dx. And then plus the integral from 0 to pi of g of x quantity squared cosine squared of x dx. Great. All right, and so now what do I notice over here? So now I notice that this, I have only two terms that remain, right? And so what are the two terms that remain? The two terms that remain are this term over here. This is the integral from 0 to pi of g prime of x, quantity squared, sine squared of x. That's one term that's there. And then over here, I have a negative g squared cosine and a positive g squared cosine. So this term over here and this term over here cancel out. And I'm just left with what? The integral from 0 to pi of g of x quantity squared sine squared of x dx. And of course, that integral is just what? G squared sine squared is just f squared. So this is just going to be something what? It's going to be something positive, because this thing over here is what? This thing over here is greater than or equal to 0 unless g is a constant, right? If g is a constant, then that says, if g is a constant, then f is a multiple of sine. So it's positive plus what? Plus the integral from 0 to pi of f of x quantity squared. So that says that the integral from 0 to pi of f of x quantity squared dx plus something positive or 0 only in the case when g is constant means that f of x is equal to a constant times sine of x. And if f of x is a constant times sine of x, this inequality over here is trivial to prove, right? It's just equal to each other. They're the same thing, right? And then what? Because you'll have a sine squared over here, and then you have a cosine squared over here, and they give you the same mode over the integral of 0 to pi. Otherwise, g prime is not identically equal to 0, and this term over here is positive, so that this term, the integral from 0 to pi of f of x squared dx, plus something positive is equal to the integral from 0 to pi of the derivative squared. So that says that the derivative squared is always greater than or equal to, in the case when f of x is c sine, to the integral from 0 to pi of the function squared. Thank you very much.